Hello, everyone, and welcome at the QSI seminar at the University of Technology, Sydney. This is the first seminar of 2021, and we have a great honor to welcome Pedro Costa amongst us. Pedro is a postdoc at Macquarie University here in Sydney, and today he will talk about quantum to classical transition via quantum cellular and automata. Thank you so much for joining us, Pedro, and take it from here.
Thanks, Maria. Actually, the honor is mine. I'm really glad for the invitation.
But they're interested to talk more.
And so this is about the result that I released in the end of the last year. This title I chose in the end of the result as soon as I got the results, and then I was different options for the name, for the title of this work. Could be other options, and how you can see during the presentation. So I'm currently, as Maria said, I'm working in the Macquarie University as a postdoc in the Dominic Barry's group. And yeah, so let's start this presentation. So before start, well, it's not control here. Okay, I would like to just point some key points of these results, which is like this is a coarse-graining procedure in terms of quantum cellular automata. And then we study this. I study this quantum. You're gonna show this QCA has a computation model to simulate the Dirac equation, and then combining these ideas, I study the semi-classical limit of the Dirac equation. Then actually, you can interrupt me if you want at the moment during the presentation, but you also can wait for at the end and then start the questions at the end. So I would like to talk about origin of this work, right? So I did my PhD back in Brazil, in the Brazilian Center of Research in Physics, and Fernando de Mello was my supervisor was my PhD supervisor, and he came out the first months of our when he starts work with him. He came with this idea. So let's study emergent phenomena via QCA. Wow, I was super excited. Let's do it, but I didn't have any idea about what the QCA, the meaning of the QCA, and also how we explore emergent phenomena on top of that. Yeah, and then I started super excited during my PhD, trying to look at that. So he had some insights about what the reasons for do this project. Is thinking like why in our daily basis we don't capture the reality of the structures. We have the lack of resolution of our eyes, right? Our detectors. He has the kind of things inside his head to have this kind of to give me this kind of project during my PhD when I study these phenomena, right? So how you lost track of what the reality of the microscopic world and how the transition happens to the macroscopic one. So this actually the inspiration coming from these results, but in Physical Review A, that's the coarse-graining that these two guys, Israel and Coldfield, they proposed the study of emergent dynamics via coarse-graining in terms of cellular automata, but the classical counterpart, right? And that was the guide for these thoughts that he had, and which is like coming with renormalization theory, a lot of interesting topics, and this really nice results. However, it didn't happen during my PhD. Because like after 1 year of studies, you see, okay, actually that's not the right way to do it, because this is not the right cellular automata version. That should be the quantum. This is not the classical counterpart of the quantum cellular automata. So the main reason, so they were trying to create things above that using previous definitions of QCA. So it was a mess and didn't happen. PhD, it does just happen after, like, and then I combined several things that I got. Actually, because of that, I got other results during this investigation in my PhD, and then I combined these results after, and then got that. And I'm going to talk about that actually in this background part, talk about the studies with this project, the idea of this project, what we end up doing during my PhD. And then I use that to do what actually this main idea of my supervisor had during my PhD. So let's start with the definition of the classical cellular automata, and the one that's not the correct one to use for the as a quantum version, okay? So this is a definition of a four tuple, and I'm gonna explain which one of these tuples are. So we start with L, which is the lattice structure that we are dealing with cellular automata. The cellular automata, I should put reference here, but back to the von Neumann that start to look at this, introduce this concept of cellular automata to study like network connections in the brain, etc., and then was developed much more by Olfran after with the concepts of physics. And then we also have the sigma, which sigma is the alphabet of your cellular automata, which means how many states you can have for each node of your lattice. And here I represented a binary one, so by two colors, white and black. Once you have that, you have to define the neighbor structure of your CA. That here I'm included the top and the bottom, left and right, but you can also include more terms on the left, more terms on the right, and the diagonal one as well. Why it is important to define the local the neighbor structure is because you have these local functions that are going to update your state according to your neighborhood. So have to in order to update your state, each of the nodes, you have to look at the neighborhood, including itself, and then going to update your state. Once you do that simultaneously, all these local functions that we call the transition function, you have the global transition function, epsilon here, that are going to update my state from time t to a time t plus 1. Okay, so now I'm going to see from this local structure, you see how you can already see that how it's difficult to like this just specific conditions are going to have these transition functions reversible all time because the domains, the content domain are different. So we have just we're limited to do reversible for all time. So that's a basic example of the CA, like one specific rule, the rule 90. So it included just in one-dimensional case, you include the left and right in the middle cells to update each state. So here's an example of a specific one here of the rule. So given that structure 0, 1, 1, you could update your state of the middle to the state 1. That's your local transition function, how it works. In this case, is like you can see that's not reversible. So that's an example how nice things you can do with the CA. So it's local structure and then simple rules, and you can have emergent complex systems. That's the reason that we start to look at this as a model to study this emergent phenomenon. So yeah, so that's what we wanted. Sorry.
Sorry, Pedro. Can I have a question? So I'm not, I'm not very familiar with the theory behind cellular automata, but this seems like seems to be related to Convey's game of life.
Yeah, exactly. Yeah.
Okay,
the game of life is one example.
Example.
Yeah, the game of life is the case of a CA with that two-dimensional case. So the neighborhood truth is different, and it also is there are rules of evolution for that, and then you can is really simple, and then you cannot predict the behavior that you have this kind of behavior that people that say like kind of the life structure, right? Yeah. So it depends on the boundary condition. The initial condition, you can have different behaviors of that. The exactly of the CA, the one-dimensional case. For a different initial conditions, you're going to have a different complex structure and measure in the end. But you cannot see from the initial state, right? So yeah. So that's the idea that we are. That's enough for me. That's answer your question, Maria.
Yeah, thank you.
Yeah. So what you're looking at, that's not the right approach. So we're looking for the one that could be reversible for all time steps in the global transition function, the epsilon, the biject for all time steps. So actually come back to the definition that Norman Margolis and Toffoli gave about the partition cellular automata. You only add after some adjectives for that, but basically the same definition. And this is really important for fluid dynamics simulations. Is the base of the lattice structure the Lattice and Boltzmann structure to do simulations in fluid dynamics. Yeah, and so this actually there's a 5 tuple to define it. So you add just some adjectives for that. And then the idea is now that you're gonna have this kind of partitioning of your lattice, your graph, etc. It can be generalized for graphs. And now the alphabet is still the same, but you think the alphabet of the cells of you got from the partition. So it is a product Cartesian of that. So they're having more possibilities for itself. And the neighbor structure is a bit more complicated to define in our picture. So that's the reason that is not clear from that. But the main reason that I included that the top part, the bottom, and the left and right and diagonals as well, because of the example that I'm gonna provide. So the idea that the adjectives that you added for the partition, cellular automata, is this kind of tessellation. So have this, your graph, your lattice, and I'm gonna give you one tessellation of that, which cover all the nodes of your, or vertices of your lattice, of your graph. And for each tessellation that you do it, you're gonna apply a specific local operator. And then starting from the beginning, so you have the sigma 0 applying the first cell, and you have a second tessellation, you're gonna interact different nodes, and then you have a different operator. You can extend that as much as you want. And then you see for these 2 tessellations cases that you can interact or nodes for each time step. So you're gonna combine sigma 0, sigma 1 to give you one time step. And it's easy to generalize for the case that you want to do a reversible one if you just have a case of sigmas are just permutation operators. If you have that, you're gonna be sure that your PCAs have reversal for all time steps. And then also it's simple to think about physical meanings for that, because you can think these permutations are acting you're going to conserve your number of particles, your model. You can also easily to consider the case you have momentum conservation, etc. So it's really these physical sides can be easily to add it here in this prescription. So yeah, so because of that, we decided to let's see if you can do this coarse-graining procedure similar they did it in terms of PCAs rather than these CAs that not reversible all time. So these are, we got this publication, the Journal of Cellular Automata, that happened the last year, but released this thing in 2018. That will actually extend these results but in terms of PCA rather than the elementary CAs. So that's the idea of this concept of where I'm talking, that I'm going to talk about the QSI as well, is the kind of studies emergent dynamics via this coarse-graining. So the coarse-graining idea that you have like this, you have some state of your PCA, and they're going to have some map that are going to have like going to lose some information, right? So, and then you have some transition function going to update my state for the time, the next time. And also going to have the same map applied before and the end of the process for another, and then we're going to lose information. And the question is if exists some epsilon tilde that's described as the emergent dynamics. So the question here is we are looking for this kind of dynamics emergent from the previous one. So here just a procedure that we developed in this classical case that actually was important for understanding how to do the quantum. So phi here is your state of a PCA. And I just think about the alphabets. Z2 means that alphabet for each element of alphabet is a binary one. And the subscript n means that I'm having any nodes or any subcells that we call it in terms of define one cell. And the first thing to do this coarse-graining procedure is you have to join these cells in S cells. You're gonna join like, and then you're gonna call, when you do this join, when you join two cells, you're gonna call that you have a supercell. So we can generalize for S cells. And the map that we're gonna apply is like we're gonna take this new supercell and gonna map to a single cell in the emergent case, in the top part. So here, this idea that we're gonna apply for all points, all supercells, this coarse-graining, and you are looking for this, and with some constraints that you have to establish this. It's not easy to establish emergent dynamics from that, because have some constraints to be established from this diagram here, which means that if you have different states in the bottom part that you're gonna map to the same state in the top one. At the end of the transition function that you're gonna do update my state, they also have to be projected to the same state. The subscript H here means that you can also you develop the coarse-graining time, which means that I'm gonna update. I have the freedom to update more time steps, and then so I'm gonna update my state from time t to the time t plus h. But in the emergent one, in the top structure, I'm gonna call just t plus 1. I just want to update state, a one-time step. So basically, just one example of that, how this is the case of the supercell is equal to. So each supercell here have composed by 2 cells, and each cell have 3 subcells, and then we have like this kind of map, and then we update and apply the same map. We update the state, and this transition function means that we only restrict the case that we have permutation operators inside the cells. And the swap operator means that you are just having swaps, which is also permutation operator, between the neighbors of each cell. And then you have like another initial state, etc. And they're gonna use the same map. And then the question is there dynamics they're gonna update for, like, consider all the constraints that I had? So that's what I did. We did in this result to show how to extend for different time scales. We got results for deterministic dynamics to deterministic dynamics. And the case for deterministic for non-deterministic dynamics was more interesting, but you have to work with less constraints that I show it, but I'm not going to talk about it. And then this method could be extended and generalized for high dimensions, the multi-particles. And then the main point that we was thinking is how to generalize that for the quantum counterpart. So let's now talk a little bit about QCA. Once you understood, if you understood the definition of PCA, it's really easy to understand the quantum version of that. The structure is the same, but now for instead of alphabet, you're going to talk about finite alphabet. I'm going to talk about a finite Hilbert space. So if you have alphabet of the binary alphabet, mean that I have work with each node represents by 1 qubit. And then if in terms of this big alphabet that you have in these cells, you're gonna just have the tensor product of these elements of each cell, each node, or in our case, each subcell. And then the only thing that you do it, the neighbor structure is the same, the tessellations that we do it is the same idea, but the difference now is W's, which is our unitary operators. Other that's other possibilities for the classical version. Also here can easily extend for the case of general quantum channels of evolution rather than just unitaries. But the point is they have to be acted locally, and then of course now we have in terms of the tensor product all these guys apply simultaneously in my lattice, and they don't commute. Sorry, they commute each W zeros with that, and then I'm gonna. By doing that, you're gonna update my QCA state from time t plus 1. So one thing that we did in these results, we show how to, you propose this definition, and you show how to translate from quantum walks, different models of QCA to quantum walks to QCA. And then I wanna focus on a particular one now. I'm gonna show the main idea of to do that, this translation for the most famous one, the model of quantum walks, the corner quantum walk. I think it's well known for everyone. But the idea that we have in this, I'm going to show the specific case, a simple case of the one dimension that I'm going to use here in this work. That we're going to have a corner quantum walk describing a one dimension path graph, for instance, or think about the one, think in terms of a graph. So you have in this graph, you have the vertex, and then the i's here, I plus 1 means the locations of the labels for the vertex. And then here, this inside the brackets means the edges connecting this vertex. So here you connect the neighbor structure of in terms of the graph. So the map works like to follow, has that. So for each vertex, you're gonna, in your QCA model, you're gonna represent by a cell. And for each, the neighbor structure, or the degree of your vertex, you're gonna give it the number of subcells in your QCA. So here you have the degree is 2, I then added 2 subcells for each cell. And then this is just a question of labels, the labeling thing. So going to the computational base of the quantum walks that you have the information about the edges and the vertex, you only have to do this map for the Hilbert's the one particle sector of the QCA, because the quantum walk you know that it just represents one particle sector of QCA, and then the Walker you only during the evolution we keep with the same the Walker that you don't appear more Walkers during the evolution. So that's the idea of QCA. We wanna, in this case, we want to provide a QCA that the particle, the excitation is conserved along the way. So it's just a question of label. So here I'm saying that if I'm in the vertex I, the excitation gonna be in the cell I, and the location of the correct location of the subcell according with the direction that is pointed out. This kind of labeling structure is important because you want to know how you're going to apply the local operators, local inter-operators in your QCA, given that you have your coordinate in your quantum walk. So the quantum walk in this coordinate quantum walk will have 2 main operators. Is the coordinate operator, then I'm going to create a superposition of the Walker for possible directions they have for each vertex. This is given by C1 here. And then have also the shift operator gonna move your Walker along with the graph, according with the position that he is located. So the transcription the translation works like that. So I have the W0s, which is our unitary operators actually in these 2-qubit systems, and then you can think in the representation of unitary representation that. In the QCA, I just, in terms of computational basis, I'm just acting non-trivially in the states 0, 1, and 1, 0. That means that I'm going to conserve the number of excitations during the evolution. So I don't, nothing happen. I can also add some phases, but nothing happen in the states, the elements 0, 0, and 1, 1. So yeah, and the second part is how I told in the coin, you have the shift operator, and then here, to have the shift operator in the QCA, you have to do a second tessellation. They're going to cover different nodes of your lattice. They're going to give the interaction. So in this one, for the shift operator, you just have to apply the swap operator in terms of QCA. And then that represents that by doing that, it represents that I have the vertex starting, the Walker starting pointing for I-1, and in the superposition pointed to I+1. And then when I apply the swap operator, it represents that I'm gonna move it for the I-1 position, I+1 in superposition, of course. But it's still pointing to the direction that I was before. And you can fix that if you wanted, adding one extra operator in both sides in the quantum walk in the QCA by doing an extra a swap operator inside of the vertex, and then is equivalent to apply again the swap operator inside each subcell that we start with, and then you're gonna make the Walker point to the other the direction he was pointing before, because I think just direction. I have a direction, it's just one-dimensional structure. So that's the map, how it works, this kind of map. So you have for the first tessellation, I'm gonna have this represents the operator that I'm applying the cells, represents the operators that I'm applying in the coin and the coin in the quantum Walker picture. And the shift, they're gonna have another tessellation, they're gonna have the swap operator according with that has to interact the correct subcells inside the cell. And the extra one to give the direction, the correct direction. So you show it that, you show it that for general graphs and different models of QCAs, quantum walks. Yeah, and this published here in the quantum information processing if you want to look more carefully at these results. Yeah. So now let's talk about the background finish, and then I promise you're going to be now. The thing now is how to stick things together, just combine things. And then to give you these results of the to give you this prescription to coarse-graining prescription for in terms of QCA. So I'm going to start giving how it can mimic how the quantum walks can be used to mimic the one plus 1 Dirac equation. So the Dirac equation, as you know, is the one proposed by Dirac to you have the relativistic regime of the electron. So then the wave function here have to be included in terms of the spinor of the electron that includes the information about the spin, the case of the different configuration of the spins, the spin up, the spin down in the case of the electron. And I have some conditions of this differential equation here. I just start in the left side with the Dirac Hamiltonian that's represented by this operator on the right here. And there's some conditions of the operator that have to satisfy it. And then, of course, I have the mass structure here of the electron I'm describing. So how I can do that with the quantum walk? So the quantum walk has back to the previous, the basic definition that you have the sector internal structure. They call it the coin space and the coordinate space. It's a tensor product of the coin space and the coordinates in the coordinate of the space. So these are unitaries gives the updated of your QCA, of your quantum walk. So we have the first operator actually just in the subspace of the coin subspace and then shift in the full Hilbert space. So in particular, let's look for the case that have this kind of structure of the coin operator. So if you do that, if you apply this coin operator, then after the shift operator gonna just do a shift in the coordinates of the space. And then the direction of the shift actually is determined by the coin information, the information of the coin structure, the internal structure of the walker. So if in the case you have in the structure, this label 0 here means that the subscript label 0 means that I have the amplitudes are related one possible direction of my lattice. And if I'm pointing for this direction, I have to shift it to a plus shifted in your amplitudes and a minus shifted for the other direction. So if you do that, you can write this recurrence relation in terms of amplitudes of the walker. And then you see that for the time, to get the expressions, the amplitudes for the time t plus delta t, you have two informations about the previous time, but they are in different locations that respect the neighbor structure of just the left and right neighbor structure that you have in one-dimensional case. Okay. So what's the trick here? The trick now is having this in terms of amplitudes. They're gonna just do a first order approximation for that, which is gonna do is just a Taylor expansion in the parameter of in the time parameter here of the amplitudes in the left side, and then I'm gonna do the same thing for in terms of the space coordinates for in the right side. And I also gonna only consider the small angle. So we're gonna also do expansion in terms of the small values of the theta here. So when you combine that, you have to, when you do this, all this kind of expansion, you're gonna just combine the first order terms, and then we're gonna get exactly this kind of expressions for sigma 0 and sigma 1, which is already in terms of the a differential operator. And then we're gonna take the continuous limit of that, which means that take the delta t and delta x going to 0. And if you now recombine this equation, the two elements of the amplitudes in one single vector, which is our spinor representation, you're gonna see that gonna appear this sigma x and sigma z here to encode these amplitudes here. So now is already clear how we can connect this with the Dirac equation that was I'm trying to show. And then of course, that's just question of label, what I'm calling sigma 1, sigma 0, sorry, not sigma, psi 1 and psi 0, with the spinor representation that you have in the Dirac equation. And then I'm going to represent these operators, alpha and beta, by sigma z and sigma x. And then that's the trick here to have to see that I'm dealing with the Dirac equation, the one-dimensional sector, is having this angle, this small angle given by in terms of the mass and the speed of light, etc. And see here, of course, you see here, just I'm using delta x divided by delta t, and then I'll be constant when in the continuous limit, and we're gonna call the velocity of your propagation. So the message, the overall message here is Okay, I showed before how to do translation for the quantum walks to QCA, and I just showed how to do the Dirac equation, how quantum walks can be used to do the Dirac equation. So the conclusion is that I can use this, the QCA model, to describe the Dirac equation. Just all I have to do is just work with this this map that I showed previously, and this are the local update state that I have to use it in the W0 that interact the cells. So that's gonna give you that representation of the Dirac equation that dimensional case. So now let's go for the coarse-graining procedure in terms of QCA. So actually this idea is actually because I'm thinking in terms of the map of quantum walks and QCA. And now it's clear because actually I'm using the same figures that I showed to show the map between quantum walk and QCA. So here you have the elastic structure in terms of quantum walks that in terms of the nodes k plus 1, etc. of your lattice, the position of your lattice in one-dimensional case, and you have the displacement between this edge by delta x. And the map in the QCA works like, as again, is that just the degree of the graph is just 2, then means that I have 2 subcells here. And which means, like in our case, it means that 1 qubit for each subcell in your big cell here. And the label is still the same of your cells. And that's the main idea. And then you can, for in terms of case and the displacement, I have the location in terms of space coordinates in both sides. So how the map works, this is kind of a Cpt map that we use it. Actually, I use it to do this, which is basically we're gonna do this kind of map. I'm gonna take for a given cell, I'm gonna map these 2 subcells for 1 subcell in the top part of your emergent one that I'm trying to look at. And so actually, if you remember of the structure of the supercells that I show in the classical case, here actually I'm using this inside because the idea that combining these 2, like in this case, this applying simultaneously these 2 Cpt maps, I'm thinking that I have 2 cells. I'm thinking I have 2 cells. I'm gonna form using 2 cells. I'm gonna have 1 supercell. And 1 supercell is being mapped for 1 single cell in the top regime, in the top part. And this is the case of the map that I explore it. And what specifically is the map is like, this is the map. They have some arguments for that, but the idea that is the case that we cannot distinguish between, I didn't put here, but I also have the sigma, the lambda, when I apply to state 1, 1, in the population like 1, 1, 1, 1, it's just going to move it to 1, 1 state, like this one here. This is gonna be the element of my matrix in the when you apply the CPT. And then the idea that you cannot distinguish, so you cannot distinguish an excitation, a particle, in this kind of have a bad resolution in my detector. So I just can see one excitation here. If I have 1, I have 2, but also if you have a bigger structure, I just gonna go for you're gonna see the 1 excitation with a small structure. And this is the coarse-graining map, which just means that I'm gonna apply this for each cell. So K means that I'm gonna apply simultaneously each cell. Yeah. So let's say back to the idea. So the idea here, the sigma, the density matrix here that I'm calling L is means that L means a general can be generalized for a given coarse-graining level. Okay. So, but the idea actually, this one should be the density matrix. In our case, it's just the case. I have a pure system, and then I start with the level 0, of course. And I'm just looking for in terms of 1 single excitation, because I want to describe it as Dirac phenomenon for 1 single excitation. And then here, how can I express the density matrix in terms of the positions that I show it in the lattice, and the A's here and prime here means the the direction that I pointed, which the subcell is located. So we can describe that. So the idea that we start with sigma rho 0, the density matrix in the level 0, and then we apply here actually, rather than apply one by one, what I did is apply L times, and then I'm gonna get in the level L. Okay, so by doing that, I could show the recursive relation expressions in terms of the level that I am L. So the elements of my here, just the elements of the population elements of my density matrix, in terms of the density matrix that I start with. And then here from the expression, you can see that actually what happened is like the information about one single element of my density matrix, the population. I have the informations about several points at the same time. I have to include all the information, all the points along the lattice that I started. And this gives the information here, the sum of S0 for to the power L minus 1, which means that I have a lattice that have this size. And the labels of my lattice starting from 0 and to the power L minus 1 here actually. And then the same thing you can have for an expression for the terms of the off diagonals of my density matrix. And then have one factor here, this is 1/3 power to the L, that comes from this map that I use it, that I have one, the square root of 3 of this part here. So actually, so to study the emergent phenomenon here, I'm not gonna include the off diagonal ones. And the reason for that is that I could show it that this kind of bound for each element of non-diagonal off-diagonal element of the density matrix. So you see that these things start to go into 0. How as I'm moving for higher levels of coarse-graining levels. I could show this upper bound, and also here as an example, the numerical example that I just did the sum of the off-diagonal elements of the density matrix I was exploring. And then it sees that starting to go into 0 as I was increasing the levels. Increase the level means I'm applying recursively this map that I showed previously. So I'm not going to include this. So that's I'm saying the semi-classical limit, because from now on, I'm just going to consider the elements of the population that I got using these maps. So the first thing that I did in the case was Massley's case of the Dirac equation. And then the idea that I also, in this case, that I'm going to show is the case of one specific initial condition. And this specific initial condition, I start with the case that imagine I have this lattice, and half of my lattices I have just excitations pointed for one direction, which means that in my lattice structure, I have the cells. And each cell have 2 subcells. From the left side of my lattice, I just have excitations in the first subcell. And for the other half of my lattice, I just have one excitation in the second subcell. So it means that if I have the Massley's case, I just, in the quantum walk sector, I just have, the only thing that's gonna happen is just the shift operator. Right, the superposition, the quantum part appears just because I start with the superposition state. And then by doing that, so Maria, sorry, how I am in my time here?
Yeah, you still have, you can go for 10 more minutes.
Okay, great. So great. And the idea, okay, I start with this kind of particular initial condition, and then I in the time 0, then I start to evolve, like, and then I focus on a particular time because nothing gonna change in the sense, because I'm gonna keep it with the same structure. And then what I could show here is that in the top part, like just looking for the population of the density matrix, this recursive relation in terms of my stated time t plus delta t, and the previous time. And then here you can see how the exchange in the structure of the coordinates that depends on how many times I'm applying the Cpt map. So this power L here means that. And then the subscript here means that I have these two sectors that they don't overlap. They are disconnected. The sigma, the zero case is the case related with the subcell, zero subcell, and have labels for each subcells. And the one means that the other subcell, which one, the zero means the left one, and then the one means the label for the right subcell of each cell. And then, of course, it's easily to see the continuous limit of that for first order approximation of this discrete operation here, which is given by that. So it's just a local transport. And then here you can see the suppressant factor to the L is a hand normalization in terms of the velocity. And then, of course, that means it's the obvious thing because you are like agglutinating your space, and then like every time that I apply this Cpt map, I'm having the dimension divided by 2, so I'm compressing. So it means the velocity at some point is gonna like remain static, right? But you can correct that by giving the update in a proper way your state before they do the Cpt map. And if you apply exactly this 2 to the L times, it means that I'm gonna go from time t to the time 2 to the power L times delta t, and then I'm gonna update my do my Cpt map, and then I'm gonna look for that will have like this update state from time t to the time t plus 3. But notice that I'm not in this study. I didn't look at specific this epsilon tilde. I just looking specific for the dynamic emergent dynamics in terms of when I got the continuous limit, which also can be, I can discretize it and epsilon tilde here, I can get the epsilon tilde from here. And then it's just swap operators in terms of a PCA, a classical partition cellular automata. So actually I'm getting that in the end because I know how to discretize this in terms of my PCA. So the most interesting case is the case that the mass is different of 0, and I didn't assume any condition, any particular condition for the initial state. It's just a general superposition. For my excitation can be in a superposition in all subcells. So this case, I don't want to show like the steps. Actually, the steps to get these results are like a lot of algebraic things have to be done to show these results, and it's not fun things to show. But the interesting thing here is that that's the idea of the connection that happens. So before here, I have the again just terms of the population elements of this matrix. Now here I don't have the subscript 0 and 1. I just merge them to the same one. Because remember, just labels for a single cell. So actually the probability associated with it being in the cell is a combination of these two subcells. So then information is already here. So they are now coupled together. And then here in the first line here, you see that the information that comes here is from this, the estimator that I start with. And then in this prescription that I show it, you have to show that this sigma 0 here, and somehow I have to show that it should be deconnected with my my estimatrix rho, sorry, not sigma, rho in the previous time. So this actually, when I take this sum inside, is exactly the density matrix that I start with in the time t. So then I can see the connection between the time in the same level, because I have to look at the emergent dynamic in the same level, not different levels, right? So then when you consider that you have this dispersion relation, so this is a constant now, considering that I just got the same, the diffuser equation, right? And then again, I can, you know that PCA is you can easily describe PCA that gives the continuous limit of the stochastic version of the random walk. There's just a stochastic version of it's just a random walk, right? So there's the stochastic version of the PCA. And then again, the factor 2 to the L is here, because here I just shown the case that I update my time t to the t plus delta t without coarse-graining time. Yeah, and these some numericals that I did that shows like the dispersion relation of the one that I start with in the sigma 0, which of course the quantum walk, you know, they have the linear dispersion relation according to the time. And the one here below is the one of you have the in the level 3 that apply 3 times the dispersion relation. And then I'm considering the mass really small mass. Okay, it means it's really small angle. And I see this, I'm fitting here. This fitting just the square root of the dispersion relation in terms of the time. So that actually is kind of respecting this bound here, this fitting that I'm getting. So it's clear non-linear anymore. Yeah, just pointed this final consideration. So here actually I showed that how to go from the classical and the classical CA actually emergent. We can show that emergent from QCA, but here I'm talking about the PCA actually rather than general CAs. And then a general procedure to study the quantum to classical transition via QCA. Just one example that I did, just one specific map. And so the idea now, and then I didn't look at for all levels. So that's our goal that I'm doing now in collaboration with people here in Macquarie, with Kevin, Alexei. The idea now is study that we can see if we can have quantum channels, quantum noisy QCAs emerging from QCAs. So we want to look for in each level, what is my quantum channel evolution that I can emerge from the unitary evolution. And then I just add a specific example for the semi-classical limit of the Dirac equation. And then here you can check the results. I just have one extra slide that I would like to, because I didn't include it because I thought that I couldn't have time. Actually, this result is not something like not expected in terms of the Dirac. What I'm showing is that the quantum walk is given the continue in the quantum to classical transition. I'm given the random walk. It's not thinking that was not expected, because here just the things that I studied during my thesis that this recursive relation in terms of probabilities for the random walk. So that idea that we have this probability to flip my walk, go to the right, and then some probability to go to the left, one-dimensional case. And then if you start to do the same thing, the recursive relation in terms of a quantum walk, you see the same kind of structure, but just I split in because you have this internal structure, which means the spin up is represent the spin up is spin down. But at the end, you can sum them to give you the probability for each vertex or each node of your cell. And you see the difference appears here in the interference terms. So if you take the continuous limit here of the random walk, you're gonna get actually the diffusion equation. And the continuous limit here, like you have to be more subtle here, because just for small masses or small values of the QE key here, you're gonna give the Dirac equation. So if in this emergent, like during this emergent phenomenon that I'm doing this transition, classical quantum, what happens that interference term is going to 0, and then of course if you put away these terms here, you're gonna exactly recover this recursive relation, and then the continuous limit is gives the random walk, the diffusion equation. So yeah, that's all that I have to say.
Thank you very much, Pedro. We now have almost 10 minutes for questions. So if people have questions, please just unmute themselves and you can ask them out loud. Also, if you don't really want to ask questions directly, you can put them in the chat, even anonymously, or just you can send them to me, and then I can ask the questions myself.
I have a question. So I don't remember which slide you had the update rule for the QCA, the 4x4 matrix. It was like W0.
Yeah. Also, do you want to see again this?
Yeah.
Okay.
So I was thinking if you wanted to compute the pre-images of that, what would the pre-image matrix look like?
I'll talk about this one, right?
Yeah, that one.
Yeah. So what is the question? Sorry.
What would the pre-image matrix look like, or like how would we get pre-images from this transition?
What do you mean by pre-image? I'm not getting it.
So I'm not sure I understand completely. So
because here actually this is okay. I show here in these slides were showing how I can use the quantum walk to mimic the Dirac equation, right?
yeah.
And then in the quantum walk is just to have this coin operator, the coin operator acting in the coin space, right?
Yeah.
And then you have the shift operator, right? And this work, the previous work that I showed that for a given coin operator that you apply in your walker, you have to apply these W zeros here, applying these 2 qubits. You have to apply in all cells simultaneously, right? And this is how we codify this, given the information of the coin, how I codify in terms of QC.
So essentially what I guess I'm asking is, the arrows going down, you're applying that rule in essentially on the QCA. So
if you what, sorry?
You're applying that update rule.
Yeah, exactly. This update
every time.
exactly.
So
that.
what would be the inverse of that?
Inverse of
so
what?
So rather than going down, like you have the down arrow, right? Go up instead.
I was talking about to do the inverse thing, like starting from the emergent one and go to the bottom one. That's what we're talking. Or
yeah. So like the idea of going backwards. So
and backwards.
It's about counting pre-images and analyzing pre-images. So I thought maybe there's some direction there.
I'm not sure. Actually, yeah, I didn't even think about it. The question?
Okay.
Yeah.
Yeah, just something. Yeah. Thanks.
Yeah. Okay.
Yeah. Okay. Yeah. Thank you, Darcy. Do we have more questions?
Yeah. Pedro.
Yeah. Hey, Gavin.
I can hear it echo because I'm right next to you.
Okay, great.
Yeah, so actually just kind of following up on Darcy's question, it sounds like maybe he's referring to the fact that if your map was an isometry,
okay,
do it as a unitary extension with a fixed input. So do you want to comment about like how isometric maps differ from like the map you have here?
Yeah. That's actually what we're planning to do, right, for next steps, right? Yeah. So, but actually, this map here, we're talking about particular for this. This map is not isometric one we're talking, right?
Right.
Yeah. So, yeah, the difference, like here, like the distance here is not isometries, right? You don't. I not keep it. The distance not keep it, right? For each level. Right, so you are reducing, you are agglutinating your space, right? So the distance of one from other sector is different, and that's the reason that we came up with these factors 2 to the L, right? So the idea is to generalize for different maps. That I didn't work with these isometric maps, and then I'm looking forward to do it and see how it's going to be the difference.
Yeah, okay, thanks.
Do we have more questions? Okay, so yeah, I should also say that now if people have more questions, Pedro is right here in Sydney at Macquarie University, and he would be very happy to talk to people in person, right, Pedro?
Yeah, of course.
Okay.
Definitely.
Yeah, okay. Yes, this talk will be also on YouTube if anyone wants to watch it later. And in this case, let's just thank Pedro for this wonderful talk one more time.
Thanks, Maria. Thanks everyone to come.